All right, well, I hope this is working. We'll see. Today we are going to do the rest of Chapter 1, where we'll talk about electron configuration of simple atoms. But before we do that, let's just take a quick look at Blackboard. I had a couple questions over the weekend about people not being able to print from Blackboard. Let me just say this about Blackboard. If you want to contact me, please don't use their message. Doesn't work. Just send a real email. That works, okay? All right, on Blackboard, this is more or less what you see. We're interested in course materials. You simply click on it. We're at week 2. We're doing chapter 2 in lab number 1. Click on this, it'll open. Week 2 assignments, and then this is lecture slides, what we're looking at today. If you simply click on that guy, you'll get this, click on it again, and after a few seconds, it'll open, show the content. If you want to print this, that's the download button. Download it. If you're using Chrome, up in the corner here, it'll probably show something. You can click on it, it will open the PDF. If you're not, just download the PDF, open it separately, and print. Remember, on Wednesday, we are doing lab number 1. Do the same exercise for the handout for lab number 1, and we should be good. You must hand in the last page at the end of lab. So please print it. Make sure you bring it with you. Any questions? All right. Way back in chapter 1, we saw this image of carbon. Nucleus in the middle, electrons around it in a cloud. At the time, I pointed out that there were 2 energy levels shown. The inner energy level is referred to as the core electrons. These are in the middle, around the nucleus, and we don't really care about them. They're just there. What we care about are the higher energy electrons. The highest energy electrons are in the outer energy level, and we're going to refer to those as valence electrons. Those matter because that's what we use to make bonds. We'll talk about bonding in chapter 3. The number of energy levels in an atom is dependent upon the period in which the atom lives. Carbon was in period 2. That's why it had 2 energy levels. Within the energy levels, you can put different numbers of electrons. N represents the energy level, therefore N is 1. 1 squared is still 1, times 2, we get 2 electrons in the first energy level. That's as many as it'll hold. Second, N squared is 4 times 2, this holds 8. Third, 3 squared is 9 times 2, this will hold 18, and so on. Now within each of these energy levels, electrons reside in something called an orbital. The simplest orbital is a spherical thing called an s orbital. The orbitals will be s, p, d, and f. Each orbital can only hold 2 electrons. So In this orbital, we can put 2 electrons. If we need more orbitals for more electrons, the next in line are the p. 3p orbitals look like this. Again, each orbital can only hold 2 electrons. Now, it's tempting to look at the p orbitals especially and say, okay, 2 electrons, I got this. We'll put 1 here, 1 there. Doesn't quite work that way. Quantum mechanics tells us that they're in this region of space, but we have no clue where. The only place it can't be is this little spot in the middle called a node. The electrons somehow get from here to here without ever going through the middle. Quantum mechanics is funny. D orbitals come next. There are 5 of them. This is my favorite, the little ring around the middle. They're kind of cute to look at. Again, each one can only hold 2 electrons. And F's are the last. This has 2 little rings around the middle. Okay, let's look at these orbitals and the way they're filled according to the shape of the periodic table. In our first period here, we can put 2 electrons. That's an s orbital. We would say hydrogen has 1 electron in the s orbital. Helium, 2 electrons in the s orbital. Going up in energy, next, we fill the 2s orbital. 1 electron, 2 electrons. Only hold 2. So over here we have the p orbitals. P orbitals, px, y, z, and again, each of these could hold 2 electrons for a total of 6. Third period, again, first 2 electrons go in the 3s. The next 6 electrons go in the 3 p's. Now, this can hold 18, can't it? But it doesn't. Has to do with the energy levels. Turns out that the 4s electrons are lower energy than the 3 p's. So we have to fill the 4s first, 2 electrons, then we can fill the 3 d's, and finally we can fill the 4 p's. Now this can get a little confusing. This again is a summary of the periodic table. 1s up here, 2s, 2p, 3s, 3p. For this course, this is all we're going to worry about. The first 3 periods. I will not ask questions about anything below that, because this is complicated enough. Any questions? Hang on 1 second here. Don't know why I had such a time getting the thing started this morning. Let's look at a real element. Carbon. Carbon's a real element. It's in the second period. Atomic number is 6. Neutral carbon has 6 electrons. Let's write the electron configuration. All right, 6 electrons to deal with. 2 of these in the first level. The other 4 in the 2s and 2p's. Here's our breakdown. Carbon is going to be here. Now, when you look at where carbon is, first thing you should say is, okay, that means the 1s is going to be full. Going to hold 2 electrons. We write that in shorthand this way. 1s2. The 2 is typically shown as a superscript. Now, once we fill the first energy level, the next 2 electrons go here in the 2s. That's going to be called the 2s2. We have 2 electrons left. 1, 2. They're in the p orbitals now. So this is 2p2. If this was an exam and I asked you to write the electron configuration of carbon, what you would simply do is say 1s2, 2s2, 2p2. The 2s electrons, these guys, these are the core. We don't care. These next 4 electrons are in the highest energy level. Those are the valence, and we care about those. Any questions? Well, quantum mechanics is full of surprises. Turns out that you can assign properties to particles. And one of the properties that's assigned to an electron is called spin. Now, classically, if you take an electric charge and you spin it, it generates a magnetic field. Therefore, electrons act as if they were little balls, even though they're not. And they're spinning, even though they're not. But they do generate magnetic fields up and down. We use little arrows to represent up and down magnetic fields. Now this becomes important because a guy named Hahn came up with a rule. And that is, if you're filling orbitals, such as the p's, what you do is you fill them one at a time with single electrons, all with the same spin. Then you go back and you fill them now with opposite spins. Now, I am not going to ask you about spins on exams, but if you go on to general chemistry, they'll talk about it forever. So I want you to at least see the concept so you know something about how they fill. If we had hydrogen and we wanted to show spins, we know that this goes in the 1s orbital. It will fill with 1 electron with 1 spin. If we go over here to helium, where we put in our second electron, we will put in the first and the second with an opposite spin. 1s1, 1s2. Let's do this on a bigger scale with fluorine. Second period, atomic number 9. We have 9 total electrons. First 2 in level 1, the rest are in the second energy level. So, here's fluorine all the way over here. Again, when you look at this, first thing you say is, 1 is going to be full. 1 has 2. 1 up, 1 down. 2s is going to be full. 1 up, 1 down. The 2 p's, we're going to have 1, 2, 3, 4, 5 electrons. They will go in one at a time, up. Then the last 2 will go in paired with opposite spins. Overall, it would look like this. On an exam, you would simply write 1s2, 2s2, 2p5. Any questions? Well, let's look at an exam question just to see that. Sulfur. Okay. Step one. Look at your periodic table and find sulfur. Well, sulfur. By George, here it is. It's an S, and it's in the third period. Now, what this means is that the first period is full. That's 1s2. The 2s is also full. The 2p is full. The 3s is full. And finally, in the p orbital, we have 1, 2, 3, 4 electrons. So we're looking for 3p4. There's our choices. 1s2, 2s2, 2p6, 3s2, and 3p4. Any questions? I put this one on an exam because every now and then when you write an exam, you want to put a really simple question on so that everybody in the room gets it right. Makes you feel good, okay? Gives you confidence. So I put this on an exam and everybody missed it. What's it supposed to? It's supposed to be the easy one. Lithium atom, atomic number 3, mass of 7, number of electrons in the highest energy shell. Okay, lithium is here. The 4 electrons are the first, these guys, right? How many electrons in the highest energy level? 1. It was supposed to be so simple. This is the valence electron, these are core. Highest energy is the valence. Now, there's a tutorial about this, of course. In this, you are given an element, and you have a bunch of blanks. You simply fill in the number of electrons. For the p orbitals, you have 3 to choose from, so work with all 3 of them. For sulfur, once again, there it is. Our first energy level is full, that's a 2. Second, 2s is full, that's 2 more. In the 2p's, we have 1, 2, 3, 4, 5, 6, but they're paired up, 2, 2, and 2. 3s is full with 2. And finally, over here with the 3p, 1, 2, 3, 4 electrons. They would go in one at a time, and then one of these is a 2 for the last. On Blackboard, it's very similar but slightly different. Okay? On Blackboard, if there are no electrons in a particular shell that's shown, you have to enter a 0. And instead of breaking down the p orbital into 3 pieces, just enter the total. So it's simple, really. Let's look at this guy down here, that's magnesium. Magnesium is here in the third period. That means the first period is full, that's 2. The 2s is full, that's 2 more. The 2p is full, that's 6 more. The 3s, this guy, has 1, 2 electrons. And finally, there are none in the 3p, so that's a 0. The differences are you must enter a 0 if something else is shown, and again, just enter the total as opposed to breaking it down. Any questions? The reason that we do electron configuration in InfoChem at all, once again, is because Chapter 3 we're going to do valence. It's important that you have a background so you understand where these valence electrons come from. So this is fairly minor. The questions will be fairly straightforward, but it's just for background. All right, Chapter 2, physical and chemical properties. Under physical properties, we will hit density, which is a big one. Chemical properties, we'll talk about the basics of chemical reactions, conservation of mass, stuff like that. Way back in Chapter 1, we talked about matter. Any substance that occupies space and has mass. Simple. Element is only one type of atom. If we take two or more elements and combine them in such a way that they have a specific and constant pattern, and you have to put in energy to separate them, we make what's called a compound. Chapter 3, we'll talk more about compounds. This is an example of one. This is methane. Methane is natural gas. Okay? It has one carbon, and it has 4 hydrogens attached. In this particular compound, the hydrogens and the carbon share electrons. When they do, they form a bond. These are valence electrons that they share. They form a bond. Every methane atom or molecule looks exactly like this one. The geometry is always the same. The bonding is always the same. There are 2 types of compounds that we will mess with. These are called molecular or covalent. Again, Chapter 3. The other type are called ionic. In these guys, we don't share electrons. This is sodium chloride, that's salt. The sodium totally donates an electron to the chlorine, and we form pluses and minuses that just clump together electrostatically. So this is an ionic compound. The other is molecular. Chapter 3. All right. Let's continue talking about substances. And now we're going to introduce mixture. If we have only one kind of matter, it's called a pure substance. That can be an element, it can be a compound. It's only one kind of matter. A mixture, we combine 2 or more substances. Now, everybody's familiar with mixtures. Mixtures actually come in 2 flavors. One is heterogeneous, which means they're just mixed up. In a heterogeneous mixture, you can separate everything simply and manually. The other type is called homogeneous. You can still separate them, but they are very uniform. An example of a heterogeneous, gravel. The test for whether this is heterogeneous or not is a simple sample test. If we reach in and we grab rocks from this section here and rocks from this section here, it will be different. These are bigger, the colors are different, blah, blah, blah. A homogeneous mixture is a different sort of thing. This is gravel. This is salt water. So salt dissolved in water. It's still just water, and it's still just salt. They're just mixed together. We know that because we can separate this very easily. If we let this just sit on the bench, slowly the water will evaporate and we'll be left with just the salt. But, going back, the sample test. If we reached in this side of the beaker and pulled out a sample, the salt and water content would be identical to a sample from this side. So identical samples means homogeneous. Once again, let it sit, water goes away, we're left with salt. All right, simple, stupid questions. Actually, let me kill one of these lights. You can see it better. This is a rock. Is a rock a pure substance? Well, you could look and say it's pure rock. But if I chipped off a little piece of this, then took a laboratory saw and sliced it very, very thin, put it under a microscope, this is what I would see. This is an aggregate, isn't it? It's just squished together to make a rock. The sample test. This section, totally different than this section. This is a heterogeneous mixture. Just squished all up into one block. These are gold bars. They all look different. They have different masses. But is it a pure substance? If you look at this on the atomic level, it's nothing but an array of gold atoms. So yes, it is an element. It is absolutely pure substance. This is sodium chloride, table salt, under a microscope. These are cute little cubes. They all look different, don't they? Is this pure? Absolutely, because, again, at the atomic level, it's nothing but an array of sodium and chlorine atoms. This array is arranged cubically. That's why these are actually cute little cubes. All right, let's do a simple question here. Look at these and just think to yourself for a second, are these pure substances, heterogeneous, homogeneous, or elements? Air, what is air? Actually, air is mostly nitrogen, 78%, 21% oxygen, and a little bit of other stuff. All of these gases are simply mixed together. So it's a mixture, right? But if we took a sample of air from this part of the room and one from this part, they would be the same, wouldn't they? The sample test tells us this must be homogeneous mixture. Pepper, we've already seen pepper. Lots of little flecks of brown and black, a little bit of white thrown in. If you were very patient and compulsive, you could take tweezers and separate these, couldn't you? It's like gravel. It's heterogeneous. It's a simple heterogeneous mixture. We saw seawater, salt water. Yes, salt water. Sample here, sample there. Same content, same composition. It is homogeneous. Sugar. What is sugar? Well, sugar looks like this. Oops. Hang on. Like this. This is a molecular model. Now on Wednesday, we're going to make a molecular model in lab. Each of these colored balls represent a different atom. Carbon is black, hydrogen is white or gray, oxygen is red, etc. Every molecule of sugar looks exactly like this. This is sucrose. This is a compound. The compound represents an absolute pure substance. Gasoline. Gasoline is a combination of different organic compounds. Aromatics, alkanes, cycloalkanes, whatever. But when you pump it out, it all looks the same, doesn't it? Because these are mixed uniformly. It is homogeneous. And finally, gravel. Well, we've seen gravel. Lots of little rocks. Easily separated, easily identified as heterogeneous. Any questions? Very simple subject, simple concept. All right, let's talk about physical properties now. We're going to start with states of matter. States of matter: solid, liquid, and gas. These are icicles. They're water. They're melting. As they melt, they form droplets of liquid water. So we have ice, which is solid. This is liquid. And filling the air around it is water in the vapor phase. So all three exist. Physical properties include appearance, density, melting point, boiling point, refractive index, whatever. Hello? Okay. When you have something that is in one state of matter, it can undergo a change, a physical change, to a different state. So here we have solid. Again, we're making liquid and gas as it warms up. We can understand this in terms of something that we will refer to as the kinetic molecular theory. That's in a couple slides. But this represents a solid, a liquid, and a gas. This little movie here represents what they look like according to the kinetic molecular theory. It will tell us that solids are little lumps like this that well, they're always moving, but they just sit there and vibrate. Don't go anywhere. Liquids, they slip, slide all over each other. And gases have no restraint at all. They simply fly around and hit the edges of the container or each other. A change in state. If we start with a solid, we can go to a liquid. Solids have defined shapes and defined volumes. Liquids have defined volumes, but they take on the shape of the container. And again, gases are totally free. They take on their own shape and move very, very rapidly. The transition from a solid to a liquid. This occurs when you put energy into a solid. It melts at what's called the melting point to give a liquid. At the same temperature, you can go backwards, freeze it, and remake your solid. We can take a liquid, make a gas out of it. That's the boiling point. We can, at the same temperature, go backwards and make a liquid. Solids do a strange thing where you can start as a solid, goes straight to the gas, also goes backwards. This is how we get frost. We have water vapor in the air. When you make frost, you don't go to the liquid first. You go directly from gas phase back to solid. Okay. Let's do a very simple problem here. This is bromine. Bromine is right here on the periodic table. It's a halogen. It's a liquid at room temperature. It forms a brown gas that is very toxic. And it can be frozen into a solid. This is a little vial that was been sitting out. This is solid. A little bit of it is melted. That's the liquid. And you can see the reddish brown fumes from the gas phase. So all three phases here. We have a melting point of -7 and a boiling point of about 59. So think about these simple questions. If we're at -20, do we have solid, liquid, or gas? Well, -20 is colder than -7, isn't it? This is below the melting point. That means we're dealing with a solid. At 80, it boils at about 59. If we're all the way up at 80, we're in the gas phase, aren't we? It's already boiled. At around 0, -0.12, well, it doesn't freeze until -7. So this means we must be a liquid. Now, once again, I put a very simple question on an exam and my class let me down. It was based on something like this. Here we have a substance that's 15 degrees above its boiling point. What is it? Everybody could get that, right? Half the class missed it. So the next class period, we went over the question. And I said, think about this in terms of a line. We have a melting point, we have a boiling point, solid, liquid, and gas. If we're 15 degrees above boiling, here's boiling, we're here. It's a gas. Another one. Melts at 115, boils at 325. We're at room temperature, which is about 25. What is it? This is our melting point. Here's our boiling point. We're at 25 degrees. We're way down here. It's a solid. This is actually the one that was on the test that distressed me so much. It melts at -45, boils at 4. We're at -36. What is it? Absolutely. Here's our melting, here's our boiling. We're at -36, which is in here somewhere. It is a liquid. Okay, simple stuff. If I give you a simple question on the exam, I'm not trying to be tricky. I don't write trick questions. Just get it right. Makes me feel good too. All right, why do things melt and boil at certain temperatures? I said it was because of the kinetic molecular theory. Kinetic molecular theory basically tells us that every substance has an inherent attraction to every other substance. These are called intermolecular forces. And basically, they make stuff stick together. Simple way to think about this. Remember these guys, buckyballs? Little round magnets. Fun to play with. They really were. Unfortunately, young children thought they were so much fun, they decided to start swallowing them. And that really messes up your intestines if you do that. So they were banned for a while. I believe some Chinese company is selling them again. But whatever you do, if you have small children, don't buy them. Anyway, you mold them into a lump. The magnetism is a model for the intermolecular forces. This is a solid. Almost. KMT also tells us that a solid is always in motion. Now this guy, this is a little movie. It's a computer-generated thing. It's a calculation, actually. Each of these little balls is assigned an intermolecular force for every other little ball. What the computer does, it will launch this guy at the clump, will transfer energy, and they'll bounce around until they eventually lose energy by hitting the wall. So each of these positions is a calculation. And after they're done bouncing madly, they start slowing down. But you see what happens? They're attracted to each other. And eventually all of these are going to come together into a lump again. They're all going to still have motion because KMT tells us they're always in motion, but they will be a lump. So, a solid. These guys are always moving because of the intermolecular forces. They're stuck together and they don't have enough inherent energy to break the forces. So they just sit there. That's a solid. If we take a solid and we put energy in, we wind up with a liquid. Now here we put enough energy in not to break the intermolecular forces, but to soften them enough that we can actually move the particles relative to each other. It still has the same volume, it just flows down. If we take our liquid and we put more energy in, then we get a gas. Here we have totally broken all the intermolecular forces, and these things just fly around merrily. Lots of space in between everything, moving very rapidly, solid, liquid, and gas. Any questions? So when a gas, these particles are very far apart. That means you can take a gas and you can compress it. Attractive forces are minimal, they basically don't exist. Takes on the shape and volume of the container. Every time it hits the wall, it transfers a little bit of energy. That's gas pressure, that's chapter 9. In a liquid, we have enough energy to make them flow, but we can't break the bonds between them. So it's not compressible, but it will take on the shape of its container. And a solid is just a lump, just simply sitting there. Now, I said that the transitions here happen at a precise temperature. Solid to liquid, liquid to gas. Melting point, boiling point. For every substance that we know of, these temperatures are unique. because the intermolecular forces between the particles are unique to the substance itself. So all melting points, all boiling points are technically unique. Now we can't measure them all, but whatever. Any questions? All right, let's continue with physical properties, and let's look at our friend Mercury. Physical property again describes the physical state, appearance, inherent properties, whatever. If we look at these little droplets of mercury, we would note that it's a metal. It conducts electricity. At room temperature, it's a liquid. And if we put some of this in our hand, we would say, my goodness, that's heavy. Well, in science, the word heavy refers to the concept of density. That is mass per unit volume. Mass per unit volume. If we express our mass in something like grams, which is typical, if we divide that by our volumes, typically cubic centimeters, again 1 centimeter on a side, this gives density, mass divided by volume. For volume, cubic centimeters, remember, are exactly the same as a milliliter. When we're talking about densities of solids, we tend to use cubic centimeters. When we do liquids, we use milliliters. 1,000 mils is a liter. Okay, let's say that we had gold. We had exactly 1 cubic centimeter of gold. We took it and we weighed it. It would be 19.3 grams. The density of gold, its mass divided by its volume. 1 cubic centimeter is the volume. This is the mass. Mass divided by volume, 19.3 divided by 1. We would write it like this, 19.3 grams slash cubic centimeter. Any questions? Let's look at some densities. Water. Most people will tell you that it's 1, but it's only 1 at 4 degrees centigrade. At room temperature, it's about 0.996. Changes with temperature. Mercury, 13.5. So much denser, much heavier than water. Put it in your hand, it feels heavy. Sulfur, about 2. Iron, about 7.9. Now these two, helium and oxygen, are gases. There's lots of zeros here. Quite often, if you're going to express the density of a gas, instead of using grams per cubic centimeter, you will use liters as your volume, and these would be, so divide this by 1,000. 0.17 grams per liter, 1.4 grams per liter. You'll note that helium is much less than oxygen. That's why helium balloons float, because it's less. Speaking of floating, this is a guy, and this is a big tub of mercury. Big tub. Hope he's holding his breath. This is a cannonball. What he's going to do is throw the cannonball into the big tub of mercury. Here he goes. The thing that's amazing here, the cannonball, which is heavy, is floating on the mercury, isn't it? Why is it doing that? Because the density of iron in the cannonball is about 7.9. Mercury is more dense at 13.5. The lighter thing floats on the heavier thing. If you crawled into this tub, you would also float. Our density is a little over 1. This is a picture that was in National Geographic in the late 60s. They were not very sensitive in those days and did not realize that this worker in the mercury plant was suffering from mercury poisoning. It's a neurotoxin. Makes you stupid. It's so much fun to play with, but it makes you stupid. Once they realized what they were showing in their magazine, they made a concerted effort to buy back every copy they could find. But before they did, I got the picture. All right, let's do a problem. We have a gas. It has a mass of 0.45 grams. We have 250 cubic centimeters of this gas. What's the density? Remember, density is just mass per unit volume. We know the volume, we know the mass. All we have to do is simply solve for density. Mass divided by volume, simply substitute in. Our mass is 0.45 grams. Our volume is 250 cubic centimeters. Do our division. 0.0018 grams per cubic centimeter. Remember, a cubic centimeter is the same thing as a milliliter. So quite often this would be shown as 1.8 grams per liter. Same thing. All right. This is a problem now. I give you a rock. And I say, what's the density of this rock? Well, you know density is mass divided by volume, right? The mass is no problem. You weigh it. That's all. But how do you do the volume of something that's irregular, like a rock? In lab, you will do this using a stopper. Not a rock, but a stopper. Again, it's an irregular shape. Well, the way you do this is called the water displacement method. Okay? It originated way back in ancient Greece. The scholar Archimedes. The king had a new crown. He suspected that the goldsmith had stuck silver in there and it wasn't pure gold. That would really irritate him. So we asked Archimedes, is this pure gold? Well, Archimedes thought about it and said, I know what the density of gold is. He knew density in those days. He was smart. I know what the density of real gold is. If I could measure the density of the crown, I could see if it was real gold or not. Okay. But how in the world would you measure the density of a crown without melting it down? Problem. The story goes that one day he crawled in the bathtub that was full, and as he submerged himself, the water ran over the sides. And he said, quote, Eureka, which is ancient Greek for, by George, I got it. Now the rest of the story is he jumped out of the tub, ran through the streets naked, screaming, "Eureka!" Whatever. What happened was his body displaced the water from the tub, and it ran over the side. Water displacement. We take the crown, stick it in a known volume of water, the level will rise. That's the volume. You're going to do the same thing, except with a rubber stopper so you don't break the glassware. This is a graduated cylinder. What you do is you put a certain amount of liquid in it and measure it very, very closely. I'm saying 22.5. You then take your rock or stopper or whatever, and you add it gently. The level rises. You now measure the new volume, 45. The volume of the rock is 45.6 minus 22.5. Simple as it can be. Mass divided by volume. We know our mass is 43. We weighed it. Our difference is our volume. Simply subtract. It's a rock, so instead of using milliliters, we could use cubic centimeters just to be more conventional. Do our division. 1.86 grams per cubic centimeter. Now, you can also write this as centimeters minus 3. Remember that something that's in the denominator, you can simply change the sign of the exponent. Same thing. And we could have left this in milliliters if we wanted to. So you will do this again with a rubber stopper. I think it's lab 3. Another problem. Ethanol is an alcohol. It's the alcohol of consumption. Its density is 0.79 grams per cubic centimeter. We have 15 cubic centimeters of it. How much does that weigh? Well, remember we did metric conversions. And I said there was an algorithm that was going to be useful. Let's do it. Given, ratio, and find. We are given 15 cubic centimeters. We're trying to find the mass. But what do we do for a ratio? Well, density is a ratio. Grams divided by centimeters. It's a ratio. Here's our given, here's our ratio, here's what we're trying to find. We simply set it up. Start with the given. Multiply by the ratio, remembering that the units of given have to be in the denominator. Cubic centimeters cancel. Multiply it out. 11.8 grams. Now, doesn't that make it simple? Remember, we also talked about significant figures, right? This is multiplication. Multiplication, we say we have to go for the least accurate number. So this has 4 significant figures, this has 3. Our answer is 3. But what about the 1? What about the 1? The 1, it turns out, is called an exact number. It's not a measurement. It's a definition. 1 cubic centimeter is 1 centimeter per side in a cube. Definition. An exact number does not count for significant figures. So yeah, we're good. three significant figures in our answer. Let's do it again. We have 999 grams of mercury, and we're holding our breath. There's its density. What's the volume? Let's do it with our algorithm. We are given grams of mercury. Here is our density. We're trying to find cubic centimeters. There's our given. There's our ratio. And suddenly we say, wait a minute. Something's wrong. The units of given have to be in the denominator, not the numerator. So what do? Just take it and flip it upside down. That's all. It's totally legal. Now grams will cancel. Multiply it out. 74 grams of mercury. Or 74 cubic centimeters of mercury. One more simple problem. We're making salad dressing. We have a liquid with a density of 0.985, another liquid with 0.873. We shake it up. We still get little bubbles. Which one rises to the top? The lowest density will float on the higher density. So B goes to the top. If you're ever faced with a problem like this, just remember the cannonball. One more problem. This one is very applicable to something you would actually do in lab. You did a calculation. You determined you needed exactly 2 grams of acetone. Acetone is nail polish remover, common solvent in organic chemistry. We know the density. What volume would you need? Go ahead, set up your equation. We are going to start with our given. We look at our ratio. We have to flip that upside down, don't we? That way our grams will cancel. Simply divide 2 by 0.791. And we need 2.5 cubic centimeters. In lab, you would measure this in milliliters. Same measurement. So density represents a class of problems. On your first exam, I can assure you, you will have a couple problems relating to density. Let's look at some old ones. We have a substance with a mass of 93, density of 1.46. What's the volume occupied? Let's do this with the formula. Okay? Density is mass divided by volume. Let's substitute. Here's our density. Here's our mass. We're looking for volume. Simple algebra, we separate out volume. And it's density divided by, mass divided by our density. Do the simple calculation. 63.7 cubic centimeters. This is also 63.7, but liters. Remember, a liter is 1,000 of these guys. Questions? Liquid with a volume. Density with a number, what's the mass? Let's do this with the algorithm. Here's our given. Here's our ratio. We cancel. To get our answer, we would simply multiply 51 by 145. We can also do it with the formula, looking for mass. Substitute. Isolate mass. Do a calculation, 74.24. Now, everyone is sitting there perplexed because nothing turned yellow. Why? This number is the same as that number, right? How many significant figures is this number? 4. This one is 3. This is 3. This is 3. This is the answer. Now this one is a combination of metric conversions, which makes everybody crazy, and simple density, which everyone can do. We're just going to calculate, we have a volume, we have a mass, but we want our units to be kilograms per milliliter. Use our formula. Density, simply take our mass divided by our volume. Mass, volume. We get 5687 milligrams per mil. But we want kilograms per mil. So we have to convert milligrams to kilograms. You can do this in your head, which is what I want you to do. There are 1,000 milligrams in a gram, right? So how many grams is this? Just divide it by 1,000. It's 5.6 grams. There are 1,000 grams in a kilogram. Kilo is 10 to the third. So how many kilograms is this? 0.0569. Just divide by 1,000. Divide by 1,000 twice, and that's your answer. All right, there are 2 density tutorials. I call them density 1 and density 2. Everybody loves density 1. Density 2, nobody likes, because it has a metric conversion built in. But we could do these in our heads. Density 1, it's a table, by George. That's it, it's a table. Something is missing. All we have to do here is remember that density is going to be mass divided by volume. So substitute in 28 grams, or 24 grams, 18 cubic centimeters, do your division, and that's your answer. Do it again. Now volume is missing. Once again, density is mass divided by volume. Now you might look at me and say, how am I supposed to remember that? It's exam day, I'm confused, I'm panicking. On the exam, you were allowed to bring 1 3x5 card. And on the front side of that, could be the back, you may write anything you want. Anything to help you in case you forget something stupid like a formula. Okay? So relax. It'll be good. Density is mass divided by volume, so volume is mass divided by density. Simply plug it in, do your calculation, we're at 51-ish. Here, mass is missing. Again, mass is going to be density multiplied by volume. Substitute, feed it to your calculator, we're at 54.7. That is density 1. Everybody loves density 1. On the exam, where do I get my exam questions? For simple density problems, I go to the tutorial, hit new problem, copy it down. Good way to practice for it. All right, density 2. Everybody hates it, but it's the same thing. It's just a word problem. Something is missing. We have a mass, we have a density, and we're looking for volume. The only issue is you're looking for a volume in cubic centimeters. This is given in milliliters, but they're the same thing, aren't they? So let's make a list of what we have. There's our mass. Given in kilograms, we want grams. Don't know our volume. Grams per cubic centimeter, same thing as milliliters. So we're looking for volume. It's simply mass divided by density. Plug in the mass, plug in the density. We get 6.5 cubic centimeters. Let's do another one. Again, word problem. We know a volume, we know a mass. We're looking for the density. Mass, our volume was given in liters, we want cubic centimeters, simply multiplied by 1,000. And we're looking for density. The calculation looks like this: mass divided by volume. Take the mass, take the volume, do our, we get a number here, but we're looking for milligrams per mil as our units. This is grams per mil. How many grams in a milligram? It's a factor of 1,000, right? Simply multiply this by 1,000, and that's our answer. So density 2 has a bad reputation, but it's still very simple. Any questions? All right, let's move on to chemical properties. Again, a property is something, it's a characteristic. Physical property is what it looks like, etc. Chemical property is going to describe a chemical reaction. A chemical change is the same thing as a chemical reaction. Let's look at an example. This is bromine. It's in a little vial because it's nasty and poisonous. This is a model of bromine, space-filling model, 2 bromine atoms stuck together. This is aluminum. Aluminum is a metal, shiny stuff. It's actually a wad of aluminum foil. Turns out that aluminum reacts with bromine. chemical change occurs. Let's watch it happen. This is done not on the tabletop, done in a fume hood. Because here's a beaker full of bromine at the bottom, poisonous bromine gas on top. Okay? We're going to take the aluminum foil and add it. It even looks poisonous. And as you add it, after a couple seconds, suddenly you see flames. You see huge clouds of poisonous gas coming out. Done in the fume hood, don't breathe it. But when it's all done, if you look here around the top, you have a crusty white solid. This is a totally new substance from what you started with. This is aluminum bromide. We have taken the reactants here. They have reacted and formed products. This is a reaction arrow. We'll talk about this in chemistry a lot. This has the same properties as an equal sign. Must have the same numbers and types of atoms on both sides, and it turns out the same mass. But that's later. All right. Chemical changes differ from physical changes. Physical change, this is what ice when it turns to water, turns to gas, but it's still water. But if we took water, we put it in an apparatus like this and passed an electric current through it, water is broken down into oxygen gas and hydrogen gas. Totally different than the water you started with. New substances. Chemical changes give new substances. An example. This is a fun reaction. We are going to take potassium. We're going to react it with water, and we're going to form new products. Potassium is K, isn't it? The little S means it's a solid. This is water, H2O. It's a liquid, L. This is potassium hydroxide, chapter 3. AQ means it's dissolved into water, aqueous. This is hydrogen, H2, and it's a gas. If we add potassium to water, it will react violently. It produces hydrogen gas. The reaction gets so hot that the hydrogen gas that's formed will react with the oxygen in the air. So it's a very fun reaction to do. These little numbers in front, those are to balance the equation. That's chapter 5. Okay, let's look at it. This is potassium metal. It's under oil, a mineral oil, because it also reacts with air. This is just water. We're going to take a little piece of this, plop it in there. Grab a nice little piece, plop it in instantly. Potassium melts, bounces around, and it's gone. If you actually use a lump of potassium that's too large, this will explode. Don't do that. Okay. Again, the burning here was hydrogen gas reacting with oxygen. Hydrogen gas reacting with oxygen is something like this. Hydrogen gas, oxygen, gas, and here we're making water in the gas phase. This is a balloon filled with hydrogen. This is a room filled with oxygen. This is somebody with a long stick. Chemists love stuff like this. This is why we all became chemists. We like to blow stuff up. Fire, whatever. It's fine. All right. Evolution of heat and light. Big Bang. Okay. Is this a physical change or a chemical change? Take a gold bar, make a sheet of gold leaf. Is it still gold? Yeah. Gold is actually the most malleable of all metals. You can pound it so it's just several atoms thick. If you see a gold dome on a cathedral or something, there's probably just a handful of grams of gold in there because they pounded in the leaf, which is just incredibly thin. Beaker of water is heated to boiling. The question is it still water? Absolutely, it's just boiling water. This is a physical change. So is this. Carbon bar is burned in oxygen, think charcoal. What are you doing here? We're making a new substance. We're making carbon dioxide. This is chemistry. It's a chemical change. All right, when I talked about a reaction arrow, I said same numbers and types of atoms on both sides and the same mass. This was actually a concept that was not understood until the late 1800s. And it's thanks to this guy, Lavoisier. Lavoisier was a French chemist. He was a noble person and did chemistry in his basement. He determined the conservation of mass law, mass of reactants must equal the mass of the products. Again, this had escaped everybody. The way he did it was a thing like this, and he took mercury in here, heated it up, made mercury 2 oxide. Now, this had to combine with oxygen to give this. So we weighed this, weighed that. Weighed the amount of oxygen that was consumed. And they were the same. If you took this, heated it up again, it could go back to mercury and release the oxygen. Again, the same mass on both sides. Here's the actual equation. Mercury plus oxygen, mercury 2 oxide. Heat this, go back to oxygen and mercury. He was considered brilliant. But sadly, he looked like this with his lovely wife. And the late 1800s in France was not a good time to be a noble person. The revolution happened, and because he was a noble person, he was arrested, taken away. Chemists all over the world said, hey, let him go. He's smart. The judge at his trial said, quote, the Republic, that's France, needs neither scientists nor chemists, and they cut his head off. Oh, for being noble. So, this is probably what's still wrong with France, but that's another thing. Let's look at a couple more questions here. Which of these represent a physical change? Lighting a match. Well, lighting a match, it burns, doesn't it? You get new stuff made. Sugar and tea. It's still sugar, still tea. That's physical. Melting of aspirin. Yes, aspirin is a real chemical compound. and it melts. That's fine. B and C are correct. All are correct. B and C are both correct. Still aspirin, still just sugar and tea. All right, what are chemical properties of carbon? It's solid at room temperature. That's physical. Insoluble in water. That's physical. Soluble in carbon 10. Most people didn't know that, but it's physical. React with oxygen. That's chemical. They form diamonds. Diamonds are just carbon. You can burn a diamond just like charcoal. Which is correct? Compounds cannot be decomposed into elements. Well, by definition, they can, but you've got to put energy into it. Both elements and compounds are pure substances. That sounds reasonable. Elements but not compounds are pure substances. A and C, this is the correct answer. One more simple density question. Cadmium, copper, and zinc are 8.6, 8.9, 7.1. We have a metal with a volume and a mass. What metal is it? How do you do this? You take mass divided by volume and get density. Look at the list. It's 8.92. That's copper. All right, today we did electron configuration, density 1 and density 2. Those are the tutorials. This is the tutorial list thus far. Remember, you must do the quiz on Blackboard to get credit. Wednesday, please be sure to print the lab handout. Please remember to bring your goggles. We are doing a real lab in D204. Any questions? We're good. Have a good day, guys.